Hello, everyone, and welcome to another virtual lesson. This is Michael Faribault from Albemarle High School in Charlottesville, Virginia. And we're going to be continuing our discussion from Friday's lesson, which was on thermodynamics. So we'll wrap up thermodynamics, and then this week we will talk about Unit 7, which is on equilibrium. A reminder to students to check out apstudents.org/exams2020 for more specific details about taking the AP exams online. A reminder that for AP Chemistry, the first testing date is on May 14th, and you can see there are a variety of different times in which, depending on where you live, you'll be taking the AP exam. There are 2 free response questions on the AP exam. And again, the information that I had presented on Friday is back again, talking about the types of things to consider for your free response questions, explaining chemical phenomena using models, theories, and representations at the particulate and macroscopic level. Again, in terms of drawing conclusions from experimental results, analyzing sources of error. Hopefully you guys have access to scratch paper, something to write with, periodic table. In today's lesson, which will wrap up thermodynamics, we will talk about enthalpy of reaction, bond enthalpies, enthalpy of formation, and Hess's law. And again, you can see the topics as well as the skills or the science practices. So including things like explain the connection between particulate level and macroscopic properties using models and representations, calculate, estimate, or predict an unknown quantity from known quantities, identify quantities needed to solve a problem. So again, we'll talk about enthalpy change, bond enthalpy, enthalpy of formation, and Hess's law. For our warm-up problem, this would be the AP practice problem that I had assigned for homework on Friday. And so this particular laboratory situation involves calorimetry. A student was assigned the task of determining the enthalpy change for the reaction between solid MgO, magnesium oxide, and aqueous HCl, hydrochloric acid. Notice that the hydrochloric acid is HCl, but the net ionic equation is shown above. So chloride ions have been eliminated as spectator ions. The student uses a polystyrene cup calorimeter and performs 4 trials. Data for each trial are shown in the table below. So part A, which is the limiting reactant in all 4 trials. Now, for limiting reactants, we have to convert the given information into moles. So since for the hydrochloric acid, we are not given grams, we are given volume, 100.0 milliliters is used in each trial. We can convert milliliters to liters by dividing by 1,000. And then 1.0, that's capital M for molarity, that would be 1.0 mole of HCl for every 1 liter. So in each trial, 0.10 moles of HCl or H plus ions were used. Now with respect to the magnesium oxide, the MgO, some trials used 0.25 grams and some trials used 0.5. Let's go ahead and pick the higher value to see what's the maximum number of moles of MgO that was used. So for 0.5 grams, convert that from grams to moles. The periodic table tells us that magnesium weighs 24.3 and oxygen weighs 16. So the sum of those 2 atomic masses give us the molar mass. So 0.5 divided by the molar mass, 0.012 moles of MgO. Now we have to consult the coefficients in the balanced chemical equation at the top here. So you can see that there is a 1:2 ratio between MgO and H plus or HCl. So if I have 0.012 moles of MgO, then I would need at least twice as much. That would be 0.024. Well, hopefully you can see that since HCl is much larger than that, it is the HCl or the H plus ions that are in excess. So the amount of moles of HCl is more than twice the amount of moles of MgO. That makes MgO our limiting reactant. So the answer to part A, magnesium oxide is the limiting reactant, and these calculations and explanation justify our answer. In part B, here we have a problem. There is an error. And this is, again, a classic style of AP question where there's laboratory situation. The error is that one of these 4 trials is inconsistent with the data in the other 3 trials. We don't have to explain why the mistake was made, but definitely some trial involves data that there must have been an error either in how to read the thermometer or just maybe just a quick calculation or something was done that was just written down wrong. So which of these 4 trials is inconsistent? And we do have to explain how we identify the inconsistent data. Now in part A, we discovered that MgO is a limiting reactant. So therefore the amount of heat produced in this experiment, because the temperature is increasing in all 4 trials, the amount of heat produced should be directly proportional to the amount of the limiting reactant, MgO. Since the total volume of the solution is essentially the same, it's 100 milliliters, and there's a small amount of solid dissolved in that. Essentially, the delta T is going to be proportional to the Q, and therefore the amount of magnesium oxide used. Let's calculate the delta T for all 4 trials. So for trial 1, 26.5 minus 25.5, that's a difference of 1. 29.1 minus 25.0, that's a difference of 4.1. And then the other delta T's are 2.1 and 4.0. So essentially what we're looking for is the trial that is inconsistent. Let's focus on, for a moment, trial 3 and 4. So in trial 3 and switching to trial 4, they doubled the amount of MgO, and the delta T is essentially doubled. So that seems like trials 3 and 4 are consistent. Now going from trial 1 to 2, they also doubled the amount of MgO, and yet the delta T has changed fourfold from 1 to 4. Okay, so something is probably wrong with either trial 1 or trial 2. Now something else we can do is we can calculate the ratio of delta T to the amount of magnesium oxide in grams. So the ratio of delta T to grams of magnesium oxide would be 1 divided by 0.25, so that's 4. 4 essentially divided by 0.5 is 8. And we realize as we go down this list here that it's trial 1 that is going to be inconsistent, because this ratio of delta T to the grams of magnesium oxide should be the same in all 4 trials. So we have now eliminated trial 1 on the basis of that ratio being different than the other 3. Our next task in this question, in part C, is to calculate the magnitude of Q. So we're going to use trial 2, although we could also use trial 3 or 4. I just picked trial 2 because it was the next one in the table. And we're going to do Q equals M C delta T. Now the C is the specific heat, in this case, of the contents of the calorimeter that is given to us as 4.18 joules per gram degree Celsius. Now these numbers right here, this is in volume, in milliliters. It's not in grams, but luckily we're assuming that the density of HCl is 1 gram per milliliter. So we have effectively 100 grams of solution. And then we have to also add either 0.5 or 0.25 to that total. So if I'm doing trial 2 and I add the 0.5 grams of MgO, that brings my total mass of the contents of the calorimeter to 100.5. And our delta T, as calculated by the difference in temperature, is 4.1. So we'll do this math, and we get 100.5 times 4.18 times 4.1. I get 1722. I'll round that off to 2 significant figures because of the delta T. So approximately 1700 joules, or 1.7 kilojoules. Notice that this is Q and not delta H. So I'm not worried about the sign being positive or negative. It's just the magnitude of heat. And again, this is heat released because the surroundings are getting warmer. When the temperature goes up, that's an exothermic process. Had you done the calculations for either trial 2, trial 3, or trial 4, you would have done the same basic setup. So mass, total mass, times specific heat capacity times the delta T, and then your answer would have been either around 1700 joules or around 880. Now, this is a different number for trial 3, but again, you could have picked any one of those trials. All right, so moving on from Q to delta H. So now, remember, delta H is essentially going to be in units of kilojoules per mole of reaction. And we should be focusing on the moles of the limiting reactant, which in this case is the magnesium oxide. So the limiting reactant, magnesium oxide. All right, so we have in trial 2, 0.5 grams of magnesium oxide. We can convert that to moles. And I'm going to go ahead and use a few extra digits here. I'm not going to round this off yet. So 0.01241. Now, the 1.7 kilojoules, that's how much heat was released. Now, the thermometer, as I said, is part of the surroundings. Since the temperature increases, we have an exothermic reaction. So the correct answer should have a negative sign for delta H. So I have negative 1.7 kilojoules divided by the moles of the limiting reactant, and I get negative 140. Again, I'm going to round that off to 2 significant figures. So had you used the data from trial 3, you would have had a smaller amount of heat, but also a smaller amount of moles. In fact, you would have had half as much in terms of Q and half as much in terms of moles. You would have gotten the same answer. So as you can see in trials 2 and 4, you would have gotten around negative 140 kilojoules per mole of reaction. But even in trial 3, because you have half as much heat and half as much moles, you still get a delta H. And again, that negative sign is important to get the correct answer. You had to know that this was an exothermic process. This negative 140 is our experimental value. Now, in our next part, we're going to calculate the theoretical or the accepted value, the accepted value from the data. And this comes from the delta H of formation. I'll be talking about an equation today in which the delta H is determined from the sum of the delta H of formation for the products minus the sum of the delta H of formation values for the reactants. See if I can squeeze that in there. Okay, so that equation, by the way, is on the equation sheet that you can use for the AP exam. So products minus reactants, and again, this delta H of formation is given to us in the table. So these are the products, Mg plus and H2O liquid. So we have those calculations. So again, these are our products. And then these are our reactants. We have MgO solid and hydrogen ions. Again, these are our reactants. So as you are putting this data into your calculator, just getting it from the table, we can then calculate our accepted value. So the experimental value was negative 140 kilojoules per mole of reaction. If we do this math, the accepted value is negative 151. So there is a difference between negative 140 and negative 151. All right, in the next part, the accepted value and the experimental value do not agree. If the calorimeter, so again, our calorimeter would look like this. We have some kind of a polystyrene coffee cup. We have a thermometer in here that's recording the change in temperature. Inside the cup is the solution. If for some reason heat somehow leaked out of the calorimeter and into the environment, okay? So if somehow heat was lost to the environment, would this help to account for the discrepancy between the values? Well, considering that the magnitude of heat that we measure would actually be less, then yes, this would account for the discrepancy. So if the calorimeter leaked heat energy to the environment, then yes, this would help to account for the discrepancy between the accepted value, which is negative 151, and the experimental value, which is negative 140. So because the delta H has a smaller magnitude when we did the calculations from the experiment, if heat had leaked out, the value for delta T would be too small. This would lead to a value of Q that is too small. And again, the magnitude of delta H would be smaller than expected. All right, well, that was our warm-up problem. And now on to today's lesson, wrapping up thermodynamics. So the enthalpy change for a reaction, the delta H, is typically either positive or negative. So positive for an endothermic process and negative for an exothermic process. These are energy diagrams. You could just be given a balanced chemical equation with a delta H, so we should know what that means in terms of the sign of delta H. So here is a reaction, a balanced equation for the combustion of methane gas. So CH4 plus 2O2, and the products are CO2 and 2H2O. Our delta H is negative 802 kilojoules per mole of reaction. When this reaction occurs, is energy absorbed or released by the system? So if we know that the negative delta H means it's exothermic, then energy is released. The reaction is exothermic because the sign of delta H is negative. Notice that we should pay attention to the phase of matter. So we have CH4 as a gas, O2 is a gas, CO2 is a gas, and in the first reaction I gave you, we have water vapor. So would we get a different value of delta H if we had used liquid water in this experiment as a product instead of water vapor? If this reaction had been written with 2 moles of liquid water on the right instead of 2 moles of water vapor, would the magnitude of delta H be less than or greater than 802 kilojoules? Again, the magnitude. So I'll give you a moment to think about that. And if you need to pause the video, feel free to do that. All right, well, hopefully you've had a chance to think about it. There is a difference between liquid water and water vapor in terms of energy. Remember that evaporation is an endothermic process in which energy is absorbed to go from a liquid to a gas. And the reverse process, condensation, is exothermic as you go from a gas to a liquid. So evaporation is endothermic. Condensation is exothermic. So what does that tell us about the relative energy values between liquid water and gaseous water? Well, gaseous water should be at a higher energy level than liquid water. And it doesn't matter whether the arrow is going up or down in these diagrams, it still shows that water vapor is at a higher energy level. So we come back to the original question. Here is a difference of 802 kilojoules going from the reactants, CH4 and O2, to the products. So if we decide to change from a gas to a liquid, then what that is going to do, it's going to put the products at a lower energy level relative to where they were before. So the answer is that it would have the delta H would have a greater magnitude than 802. Now I can tell you this, that essentially the difference between 2 moles of water vapor and 2 moles of liquid water is approximately about 88 kilojoules. So in fact, the delta H would be around negative 890 kilojoules. What I'm just showing you here in the fact that I can add these 2 steps together, negative 802 and negative 88, and get negative 890, that is actually an example of a concept that I'll be talking about at the end of today's lesson, which is called Hess's law, where you can take 2 different steps, add those 2 steps or those 2 reactions together, and you can add the delta H values together. Something else I'd like to mention with respect to a thermochemical equation where you have coefficients and you have a delta H is that we can do essentially stoichiometry. And now we can use, in our stoichiometry calculations, we can use the delta H as a magnitude of heat. There are 802 kilojoules of energy released for every, for example, 1 mole of CH4. Or you could say that there are 802 kilojoules of heat released for every 2 moles of oxygen consumed. So we're just using mole ratios to convert from one chemical to another, but we can also use the ratio of the heat. So when it says mole of reaction, that means it's not specific to moles of one particular chemical, but all of the coefficients in the balanced chemical equation with their coefficients relating to number of moles. You can then relate it back to this negative 802, the change in enthalpy. All right, so in this problem, in terms of stoichiometry, suppose that we have 7.50 grams of methane, CH4, and it reacts completely with excess oxygen according to the equation shown above. How many kilojoules of heat or thermal energy would be released? Again, feel free to pause the video, work this problem out on your scratch paper, and then press play and check to see if your answer is correct. The first thing that I am going to do is convert grams to moles. So the periodic table tells me that carbon weighs approximately 12.01 and hydrogen weighs 1.008. So I have 4 hydrogens and 1 carbon. So my molar mass of CH4 is 16.042. But now I have to convert into kilojoules of thermal energy. So I'll put 802. I'm not worried about the negative sign right now because it's the amount of heat that is released. 802 kilojoules on the top, 1 mole of CH4 from the coefficient in the balanced equation on the bottom. And then I would do this math. So 7.5 divided by 16.042 times 802, and I get my answer. All right, we'll try one more like that. This time I will give you grams of a different chemical. Suppose that 45.0 grams of oxygen reacts completely with excess CH4. According to the equation shown above, again, how much heat is released, how many kilojoules of thermal energy? There are 32 grams of O2 in 1 mole. Now, the most common mistake that students would make is, especially after they saw this last example that I showed you on the previous screen. All right, and they would do that and get their answer, but it would be incorrect. So if you're going to talk about kilojoules per mole of reaction, you have to focus on the coefficients in the balanced chemical equation. So be careful that you don't make that mistake, which is to neglect the coefficients from the balanced chemical equation. All right, so we have to then get 2 moles of O2 for every 802 kilojoules like that. Now I could show this a little bit differently and get the same answer. So watch me do it like this. There are 2 moles of O2 for every 1 mole of reaction. And there are 802 kilojoules for every 1 mole of reaction. That way you might, if the bottom method is easier for you, you can try it that way. It's the same example in terms of numbers, but just to kind of remind you why we do that. All right, well, we were given the delta H for the combustion of methane. Now we have the combustion of a different chemical. This is propane, C3H8, but now we don't have the delta H. So this is going to be a review of some concepts that I had explained on Friday's lesson talking about calorimetry. Suppose that 1 gram, 1.00 gram of propane is combusted or reacts completely with oxygen according to the equation shown above. The heat that is released from this combustion reaction is completely transferred to a container with 250.0 grams of water inside. The temperature of the water increases from 20.0 degrees Celsius to 68.2 degrees Celsius, and they give us the specific heat capacity of water. So if you remember, mc delta T, Q equals mc delta T. Let's calculate the amount of heat released in this experiment and the delta H. Okay, so we'll start with the Q. So Q equals mc delta T. We know that the mass of water was 250.0 grams. We know the specific heat capacity was given to us as 4.18. And the delta T would be 68.2 minus 20. That's a difference of 48.2 degrees Celsius. I will do this on my calculator. And when I did this, I got 50,369. I rounded this off to 3 significant figures based on the delta T. So 50,400 joules, or 50.4 kilojoules. I'm not worried about the sign being positive or negative. This is just simply the amount of heat released. Now, 1 gram of propane was not used in this calculation, but that is how much propane was burned. Let's convert that into moles. So for the delta H, let's convert grams of propane into moles. And I did the conversion using C3H8, so 3 times the molar mass of carbon and 8 times the molar mass of hydrogen gives me 44.094. I'm not done yet, but that is my first step, is to convert grams to moles. We go back to the amount of heat that was released, and I'm going to go ahead and put a minus sign because this is an exothermic reaction. How can we tell? Because the temperature increased. Thermometer is part of the surroundings. Combustion reactions are typically exothermic. And we end up with negative 50.4 divided by the number of moles, which, by the way, even though there is a 1 that is understood to be a coefficient here, there are other coefficients as well. So this delta H that we're talking about is not necessarily per mole, but rather per mole of reaction. Okay, and I did this math, and I got negative 2,220, rounding off to 3 significant figures, and that's kilojoules of energy released per mole of reaction. Okay, so our next topic in today's lesson is on bond energy or bond enthalpy. So what you are looking at right now are a variety of chemical bonds. We have single bonds, double bonds, triple bonds, and then there is bond enthalpy listed next to each bond. So what exactly is bond enthalpy? It is the energy required to break that particular bond. It can also represent the amount of energy released when that bond is formed. So it is endothermic to break a bond. It is exothermic to form a bond. So the magnitude of energy either absorbed or released depends on whether you are breaking or forming the bond. Here we have the combustion of methane again. We saw this earlier in the lesson, and the delta H is given to us. Let's see if we can get the delta H from bond enthalpy values. So I have to actually draw out the Lewis structure of these molecules to decide what exactly do the bonds look like on both the reactant side of the equation and the product side of the equation. Well, CH4 is a rather simple molecule with 4 single CH bonds. The oxygen molecule happens to be, if you draw the Lewis structure, an oxygen-oxygen double bond. And with a coefficient of 2, that means we have 2 oxygen molecules for every 1 molecule of methane. On the product side of the equation, we have 1 molecule of carbon dioxide, which contains 2 carbon-oxygen double bonds, if you draw that Lewis electron dot structure. Each water molecule is just H2O, but we have 2 of them. So for a grand total of 4 oxygen-hydrogen single bonds. So I have bonds that are being broken. And again, that is an endothermic process, so a positive value. I have bonds that are being formed, and that would be an exothermic process or a negative value. So what I can do now is I can consult a table of bond enthalpy values, and I can find the particular bonds that I'm dealing with in this particular problem. So we have a CH single bond, 413. This is the bond enthalpy in kilojoules per mole. We have an oxygen-oxygen double bond, 498. We have a carbon-oxygen double bond, 799. And we have an oxygen-hydrogen single bond, 463. So how many CH bonds do I have? Well, I have 4 of them. So I'm going to do the math, and you can kind of follow along here. 413 times 4 is 1652. Again, all these would be in units of kilojoules. I have 2 oxygen-oxygen double bonds. That's 498 times 2 is 996. So my grand total, 2,648 kilojoules of energy absorbed when those bonds are broken. All right, on the product side, I have 2 carbon-oxygen double bonds. So 799 times 2 is 1598. I have a total of 4 oxygen-hydrogen bonds. So 463 times 4 is 1852. That's a grand total of 3,450 kilojoules. Now remember that since the energy is released when bonds are formed, I am going to put a negative sign on that value. So we have to add the negative sign to the bonds formed total because forming bonds is an exothermic process. So 2,648 minus 3,450, that's the math that I am doing. So effectively the delta H is going to equal the total sum of the bond enthalpies for the bonds that are broken minus the sum of the bond enthalpies for the bonds that are formed. Now, if you do this math, 2,648 minus 3,450, you should get, hey, look at that, negative 802. That was the number we already had earlier. So negative 802. This is a good estimate of the delta H for the combustion of methane. All right, let me jump to some AP practice problems on this particular topic. So you're looking at part of a question. This is part B of a AP free response question, and you can tell that we're going to be using bond enthalpy values because there is a table given. It says in part B of this question, using the Lewis electron dot diagrams of fulminic acid and isocyanic acid as shown in the boxes above, and the table of average bond enthalpies below, determine the value of delta H for the reaction of fulminic acid, HCNO, to form isocyanic acid, HNCO. So I'm going to go ahead and highlight. Here's our equation, bond enthalpies for bonds broken minus bond enthalpies for bonds formed. I'm going to highlight the HC bond in yellow. I'm going to go find that in the table. That's 413. And I'm going to write that down. I'm just going to keep track of all of my bonds, kind of going one bond at a time. The next one I'm going to highlight is the CN triple bond. I find that in the table. That's 891. So I'm going to write that down. And then in the fulminic acid, we have a nitrogen-oxygen single bond. And there it is in the table. That's 201. So that would be my grand total of energy absorbed because those bonds are broken. Okay, moving on to the other molecule, the isocyanic acid, I have an NH single bond, which comes in at 391. I have a nitrogen-carbon double bond, and that is listed as 615 in the table. And then I have a carbon-oxygen double bond, which, according to the table, comes in at 745. So we have a total of 1,505 for the energy absorbed. And we have a total of 1,751 for the energy released. So 1,505 minus 1,751 gives me my answer. In this case, the delta H is negative 246 kilojoules per mole of reaction. All right, let me jump to another AP practice problem from a different AP exam. And in this one, they actually tell us the delta H. It's 1.6 for this reaction here. What we don't know is the bond energy or bond enthalpy for the bromine-chlorine bond. So we're going to still use the same equation, but just plug in everything we know and solve for what we don't know. So it would be on the left side of the equation, there are 2 BrCl molecules. So we're going to be breaking 2 BrCl bonds. And on the right side of the equation, we have a Br2 and a Cl2. So we're going to be forming a Br-Br bond and a Cl-Cl bond. All right, they gave us the delta H was 1.6, and that is equal to 2 times whatever the bond enthalpy of a Br-Cl bond is. We don't know that yet. That's the question mark in the table, minus 193 plus 243. So we'll go ahead and just combine the numbers. So 2 times the Br-Cl bond, which we don't know yet, is equal to 1.6 plus 193 plus 243. Now, be careful. that you don't get to this point and say, okay, I've got my answer. My answer is 437.6. So again, sometimes when students are going too fast, they forget little details. So in this case, that is not the answer because we still have the math to do. We have to divide by 2. So the correct answer is actually half of that value. Okay, so the correct answer is approximately 219 kilojoules per mole for the bond enthalpy of the BrCl bond. All right, so again, those were AP practice problems. The next concept I'd like to talk about is enthalpy of formation. So now you don't see bonds, you actually see entire formulas of chemicals. We have carbon monoxide, carbon dioxide, water vapor, liquid water, hydrogen, oxygen, CH4. These are actually substances. So what is the enthalpy of formation? Well, the standard enthalpy of formation, which has the symbol delta H with a superscript 0 for standard conditions and a subscript F for the word formation. This value represents the change in enthalpy associated with the formation or synthesis of 1 mole of that particular compound from its elements. Now, if you're forming a compound from its elements, for example, carbon monoxide would be formed from carbon and oxygen. CH4 would be formed from carbon and hydrogen. NH3 at the bottom of the table there would be formed from nitrogen and hydrogen. It might stand to reason that what if you already are an element? So I've got 2 elements in the table, hydrogen and oxygen. It's impossible to form an element from an element. You already are an element in your standard state. So by definition, the standard enthalpy of formation for a pure element in its standard state is equal to 0. All the other values in this table are non-zero because they are referring to compounds as opposed to elements in their standard state. All right, let's give you some specific examples of what does it mean when I talk about the formation of. So this is carbon monoxide. It would be formed from 1 mole of carbon and 1/2 mole of O2. So the delta H is the energy that is associated, the change, with the formation of 1 mole of that substance. If it were carbon dioxide, 1 mole of carbon plus 1 mole of O2, again, the energy associated with that particular synthesis reaction. For water, 1 mole of hydrogen plus 1/2 mole of O2 leads to 1 mole of water vapor. If it was methane, 1 mole of carbon plus 2 moles of H2, again, CH4 is being produced, and that's the delta H associated with that. So as I mentioned before in the warm-up problem, you have an equation, and again, that would be delta H of formation for the products minus the delta H of formation for the reactants. So if I was given an equation, in this case, the combustion of methane, and I had to calculate the delta H, not from the bond enthalpies like we did earlier, but from the delta H of formation, the standard enthalpy of formation, then what I'm doing here is I'm calculating, and again, these are delta H of formation values. I'm doing products minus reactants. So CO2 is right there. There are 2 moles of water vapor, so I've got that. And then minus the reactants, I have the CH4, which is right here. And then since oxygen happens to be by definition an element, which is 0, then I really just have 2 times 0 over here. So that's products minus reactants. Again, this is not about bonds broken minus bonds formed. This is about the delta H of formation for the products minus the delta H of formation for the reactants. So again, it's one of the differences between those 2 equations is that we are talking about bonds versus the entire substance as a whole. All right, if I go ahead and finish off this math, no big surprise, we get that negative 802 that we have seen earlier. So again, this is the combustion of methane. Now, earlier in this lesson, I had given you the combustion of methane, and I had said, if this reaction had been written with 2 moles of liquid water instead of 2 moles of water vapor, and we had talked about how the delta H would be greater in magnitude. In fact, it was roughly about 890 when I was trying to show you earlier on the the slide, I was talking about how the difference between liquid water and gaseous water is about 44 kilojoules. So if I have 2 moles of liquid water and 2 moles of gaseous water, that difference between these two is around 88. Let's go ahead and do the calculations. Notice that we have to pay attention to the phase of matter. So we are not using negative 241.8, we're using negative 285.8. And again, that came from the table of standard enthalpy of formation. And sure enough, I get a magnitude that is different than 802. I get around negative 890. So if you are given a table of bond enthalpies, okay, do not confuse the bond enthalpy with heat of formation. Those are two different equations, okay? So we're going to be careful that we're not confusing these two concepts. So let's see an example of heat of formation, which is different than bonds broken minus bonds formed. Heat of formation is products minus reactants, okay? So we can tell that this is referring to standard enthalpy of formation. These are not bond energies, but the enthalpy of formation for the formation of an entire substance. And they gave us an equation at the top, and they already gave us a delta H. They give us another equation, and it says, will the combustion of 2 moles of C3H6 release more or less heat than the combustion of 2 moles of this vinyl chloride, this C2H3Cl? So we're going to do products minus reactants for this particular equation. So 6 times CO2 is right here. 6 times water vapor is right here. I'm just getting this from the table. And then we have minus the reactants, 2 times 21. That comes from this. And again, 9 times 0, because that was just oxygen. So we have now gathered all of our data. We have now plugged in the information for this particular equation in the red box, and we get a delta H that is larger in magnitude than the other one. So the question had said, determine whether the combustion of 2 moles of propene, which is C3H6, releases more or less energy than the combustion of 2 moles of vinyl chloride. So again, because 3858 is a larger magnitude than 2300, the combustion of 2 moles of propene releases more energy. Okay, so again, do not confuse delta H of formation and bond enthalpy. Okay, so here you can definitely do the products minus reactants if you are given delta H of formation, but over here it's going to be different. It's going to be bond energy. So you have the bonds broken, which is a positive number, minus the bonds formed. So a common mistake that students make on the AP exam is they confuse these two equations. So make sure you are clear in your mind about what you're doing with the data. All right, Hess's law has to do with adding 2 or more reactions together. And if you add reactions together, you can also add the delta H values together. So the delta H is simply the sum of the individual delta H values for the reactions that you are adding together. There are some simple rules associated with changing these thermochemical equations, and these are kind of obvious rules. If you decide to reverse the direction of a reaction, you have to change the sign of delta H, because now it changes from being endothermic to exothermic or vice versa. If for some reason you have to go into the coefficients and multiply each and every coefficient by a particular constant n, then you would have to also multiply the value of delta H by that same value n. And as I mentioned, when you add 2 equations together, you would add the total of the delta H values. So here you're going to see a Hess's law problem. This is not from a particular AP chemistry exam, but it's simply a good example of the different manipulations that you have to do. So we're going to call this equation, equation number 4. This is our target equation. This is an equation for which we don't know the delta H. But can we combine equations 1, 2, and 3 in such a way that when we add them together, they will equal equation 4. So I'm going to go ahead and analyze the chemicals that are in equation 4. We have 2 moles of carbon. I definitely see carbon up there in equation 2. We have 1 mole of hydrogen. I definitely see hydrogen up there in equation 3. And we have 1 mole of C2H2, which is called acetylene. I see that chemical featured in equation number 1. So what I'm going to have to do with equation number 1 is that I've got the C2H2. It's on the wrong side. It needs to be on the right side of the equation as opposed to on the left side. I'm going to have to reverse equation number 1, which means when I flip the equation around, the magnitude will remain the same. It'll still be 1256, but when I switch the location of reactants and products, I change the sign. So as I flip equation 1, now the delta H is positive 1256. Okay, there is carbon featured in equation 2, but unfortunately it's not the right coefficient. So I need there to be 2 moles of carbon in my target equation, equation 4. I'm going to have to take equation number 2 and multiply each and every coefficient by 2, which means that now the delta H will still be negative, but instead of negative 394, it's going to be negative, well, twice that, so negative 788. So I multiplied each coefficient by 2 as well as the delta H. And now in my third equation, I see the hydrogen, but unfortunately it's not the right coefficient either. So I'm going to have to take that third equation and multiply each and every coefficient by 1/2 or 0.5. So when I do that, the negative 484 will also be multiplied by 1/2. So now I'm going to have negative 242 when I multiply equation 3 by 0.5. So to verify that everything looks good, let's cross off all of the things that are not going to be showing up in the final equation because they are featured on both sides. Kind of like when you eliminate spectator ions in a net ionic equation. I see 2 moles of CO2, and there's 2 moles of CO2 on the other side of the equation. So that gets eliminated. I see 1 mole of water and 1 mole of water on opposite sides. I see 2.5 or 5 over 2, 2.5 moles of oxygen. There's 2 and there's another 1/2. So 2.5 moles of oxygen on opposite sides. But everything else, the 2 moles of carbon, the 1 mole of hydrogen, and the 1 mole of C2H2 acetylene, those are the only chemicals that are left. So if I add 1256 plus negative 788 plus negative 242, I will get, in this case, the delta H for equation 4, which works out to be positive 226, and that's kilojoules per mole of reaction. So that's an example of Hess's law. You can manipulate equations by flipping them or multiplying by a certain value and then adding them together to equal a new equation. And you just add the delta H's together. So in today's lesson, which again covered thermodynamics or thermochemistry, we talked about enthalpy change for a reaction, talked about bond enthalpy. Again, that's bonds broken minus bonds formed. Talked about enthalpy of formation, so products minus reactants, and talked about Hess's law. So now, before I finish, here is your homework problem for tomorrow. So tomorrow, Mr. Byrne will go over the answers to these questions from an old AP exam. So this is the first slide. You want to take a screenshot of that or pause the video. So we're going to do several parts of this question. This is the first one. And then here is the next one. And here is the next one. So we're doing parts C, D, E, and F. All right, so again, tomorrow's lesson, we will talk about the answers to this particular question and introduce equilibrium, which is unit 7. So a reminder to check out the helpful chemistry resources in the video description. This has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. Thanks for watching, and remember, if you have not contacted the College Board about your needs for either mobile tools or connectivity, the deadline for contacting the College Board, you can go to cb.org/check. The deadline is April 24th. All right, have a good day. Thanks for watching.